Okay, these are the solutions for the 5 questions that I had assigned in class. So this is number 20, this is August 2017, this is number 26. So we have a rhombus, and we know that in a rhombus, all sides are equal. We also know that the diagonals bisect each other. And we also know that the diagonals are perpendicular. Okay, so PR is 16, and PR is this line right here. So since we know the diagonals bisect each other, we know that if it's 16, each of these pieces is 8. And the other line, QS over here, that one is equal to 30. So if that's bisected as well, each piece is 15. So if you pull out one of the triangles, so I'm just going to pull out the top one, it looks like this. Right, this is P, and this is Q, and it intersects at T, and here's the right angle. So we know that this is 8, and this is 15, and we're going to find this side. So you can use the Pythagorean theorem. Take the square root of both sides, and x equals 17. So that's this side over here. But in a rhombus, we know that all sides are equal, so that means that every side is equal to 17. And we're trying to find the perimeter, so the perimeter just means to add all the outside pieces. So it's going to be 17 times 4 pieces, and that is going to give you 68. And that was the answer for that one. Okay, so this is number 31. And so we first have to get this in the correct form, and we're going to take this negative 8y over here, and we're going to move it over to the other side. So it becomes positive 8y. Okay, and then I know I'm going to have my 2 parentheses, and they're both going to be squared. The first one's going to have an x, the next one's going to have a y. So, let me get another color. Okay, so I'm going to look over here, and I see I have a negative 6, so that means it's going to be a negative. And you're going to take that 6, and you're going to divide it by 2. You always divide by 2, so that's going to give me 3. And then over here I have a plus sign, so I'm going to carry down the plus sign. And here's an 8, and 8 divided by 2 is 4 as well. Okay, and then we still have the 56 on the right side, but now we have to go back over here to this negative 3 and square it. That will give us 9, so we have to add 9 to the right side. And then here's 4, you have to square that, and you're going to get 16 on the right side. So based on this, we can see that the center of the circle is going to be 3, negative 4. And I got that from taking the opposite sign of negative 3, would be positive 3, and the opposite sign of positive 4 would be negative 4. Next, we need the radius. If you add all 3 of these numbers together, you're going to get 81. So to find it represents r squared. So to find the radius, you're going to take the square root, and you're going to get that r equals 9. Okay, here's number 32. So I already graphed the triangle, and we're being told that there are points A and B, and those are the midpoints of PQ and QR. So we're going to find those midpoints. So PQ is located right over here. That's PQ. So P is negative 3, negative 1, and Q is negative 1, 7, and we want to find the midpoint. So to find the midpoint, you just take the two x values, negative 3 and negative 1, and you're going to combine them and divide by 2. Then you're going to take the y's, and you're going to combine them, you're going to divide by 2, and that will give you your midpoint. So you're going to get negative 4 over 2, which is negative 2, and you get 6 over 2, which is 3. So negative 2, 3, right here, that is going to be point P. That's the midpoint. No, it's not point P. Sorry, that's point A. Okay? And then we have to do the same thing for Q and R. So let's start again. So Q was negative 1, 7, and R was 3, 3. So we're going to combine the two x's and divide by 2, and then we're going to combine the two y's and divide by 2. So that will give us 2 over 2, which is 1, and 7 plus 3 is 10 over 2, which is 5. So at the point 1, 5, right here, I just lost that one. 1 and 1, 2, 3, 4, 5, right here. That is going to be our point B. Okay, so it says that those are midpoints, and we need to prove that AB, just erased my beautiful picture, that AB, let me get those points back. It was 1, 5, and, okay, my picture's back. Alright, so we need to first prove that AB is parallel to PR. So all you have to do is find the slopes. So the slope of AB, I'm just going to count up and over, so I'm going to count, let me get another color so you can see better. So I'm going to count up 2 and over 3. So the slope is 2 over 3. Then we do the slope of PR, and so I'm going to count up 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6. So 4 over 6. But 4 over 6 is equal to 2/3. So you're going to write, since AB and PR have the same slopes, they are parallel. Okay, I hope you can read that. Okay, but we're not done yet. I'm going to get another color, because we also have to prove that AB is half the length of PR. Okay, so we prove how long a line is by using the distance formula. So first we're going to need the length of AB. So A, we said, was the point -2, 3. A is -2, 3, right? I think 1, 2, yeah. And B is 1, 7. No, 1, 5, I think. Let me just double check that one. 1, 2, 3, 5. 1, 5. Okay, so we're going to use the distance formula for that. So it's going to be y2 minus y1 squared plus x2 minus x1 squared. So this is going to give us 4, and that's going to give us 9, and we get radical 13. Okay, then this was B over here. Okay, so radical 13. Now we have to find the length of PR. So P is the point -3, -1, and R is 3, 3. So we're going to do the distance formula again. y2 minus y1 squared plus x2 minus x1 squared. And this is going to give us 4 squared, which is 16, and 9 squared, which is, 6 squared, which is 36, and that is going to give me the square root of 52. So it looks right now like these are unrelated, but radical 52, if we simplify it, is equal to 4 and 13, and the square root of 4 is 2. So 2 radical 13 and radical 13, yes, PR is twice as big. So I'm just going to erase this so we can write our concluding sentence. So you're going to say that AB equals radical 13, PR equals 2 radical 13, therefore, remember that's the notation for therefore, AB is half the length of PR. Okay, so here's number 33, and I'm just going to say up front, this one was pretty difficult. Okay, so I'm going to do one thing at a time. So they're telling you that chord BC, that's this chord here, is parallel to secant ADE, that's this one. So right away, you should notice then that you're going to have alternatory angles here and here. So you're going to write angle BCA is equal to angle CAD, and your reason would be alternate interior angles are equal. Okay, so that's the first thing. Okay, so if we want to try and prove that the two triangles are equal, and what two triangles am I talking about? I'm talking about this one, this yellow one, and I'm talking about this orange one. Okay, that's what we're going to do. We're going to try and prove that those two triangles are equal. Okay, so we just found one pair of angles, so that's good. Okay, next, we know that AOC is a side of both triangles. So we can say AC is equal to AC, and that is the reflexive property. Okay, so what do we have so far? We have an angle, and we have a side equal to an angle and a side. So we just need one more thing. Okay, so here's the next thing. Let me get another color. Okay, if you look at this angle over here, ABC, sorry, that's Jojo barking in the background, that is an inscribed angle that intercepts a diameter. Therefore, this is a right angle. So angle ABC equals 90 degrees, and the reason would be an inscribed angle that intercepts a diameter is 90 degrees. Okay, and the reason for that, just in case you forgot, is it ends here and here, meaning, we get one more color, that the arc, which is this piece here, is 180 degrees, so it's intercepting an arc of 180. An inscribed angle is half of the arc it intercepts, so that means that it's 90. Okay, now here's the next thing. If you look over here at this angle, right here, ECA, that is a diameter that is intercepting with a tangent. And when that happens, we have a right angle. So we're going to say, get rid of this, that angle ACE, I have to say this is like one of the hardest proofs I've seen on the regions. ACE equals 90 degrees, and you're going to write when a diameter, and it could also be just a radius, when a diameter intercepts a tangent, they form a 90-degree angle. Okay, so that's a rule that a diameter that intercepts with a tangent, or a radius that intercepts with a tangent, will always be perpendicular. Okay, so now you can see we have two right angles. If I could erase this, that'd be great. Come on. Alright, here we go. Alright, so we have two right angles, and of course, all right angles are equal, right? So we're going to say angle ABC equals angle ACE, and your reason is going to be all 90-degree angles are equal. Now the good news is we just bought ourselves another angle for each side here. So if you look at the picture, get one more color here. We have angle, we have angle, angle, side, and we have, for this triangle, we have angle, okay, whoops, as I'm saying this, I'm realizing that doesn't make sense. On this one, we have angle, side, angle. So we don't have angle, angle, side for both. Well, we have angle, angle, side, but it's not in that order. Okay, so let's do some work and fix this up. Try to erase this. Okay. So we've said before, if you have two angles equal to two angles in two different triangles, the third angle must be equal, because 180 minus those two angles would equal to 180 minus those two angles. So based on that, and I'm just going to kind of erase this to make it a little bit neater so you can see what's happening. Get a better color. Okay, so we said this was reflexive, that was our side, and we did alternary angles, and we said these are equal. And we have this right angle, and we have this right angle. Okay, so then that would mean that the leftover angle, so we're going to say this one that I'm coloring in, is equal to this one. Okay? So now you can see that we have angle, here's an angle, angle, and then here's the side. And if you look at the top triangle, you have angle, angle, and there's the side. Okay, so first we have to say that those angles are equal. So we're going to say that angle BAC equals angle CEA. There's lots of different ways that you can say this. Probably the easiest way you can say it is if two angles of a triangle are equal to two angles of another triangle, then the third angles will be equal. Okay? So we first have to say that why those are equal. Okay, now that we know that they're equal, now we can say angle, angle, side for both of them. So let's write that up. Warned you this was a hard one. Alright, so triangle ABC is congruent to triangle ACE because of angle, angle, side. Okay? So we did all that, but what is this question asking? It's saying to prove this proportion. So we know that in similar or congruent triangles, the corresponding sides will of course be in proportion. So if you look at this side over here, BC, I'm just going to write that, BC, over CA, because that's what they're asking for right here, CA, will be equal to, now we have to find the side that corresponds to BC. So BC was the side between the right angle and this open angle. So if you look at the bottom triangle, the side that's between the right angle and the open angle would be this. So BC of the top triangle corresponds to AC of the bottom triangle. And CA, right here, CA, that is the line right here, and that's between these two non-right angles. If you look at the triangle on the bottom, you can see that this is you're looking for the side between the one and this open one. Okay, hang on, because they don't even care about that side. They care about AB, so let's write AB. Okay, so we could have set up a different proportion, but we want to do the one they want. Okay, AB is right here. AB is the side between the right angle and the filled in one. And so if you look at the bottom triangle, the side that's in between the right angle and the filled in one is CE. And notice that this thing matches this perfectly. So you have to write your reason why this is true, and you're going to say, I'm going to write it up here where somewhere. If two triangles are congruent, then their corresponding sides are in proportion. Okay, that one was a doozy. That was quite difficult. Okay, we got one more to go. Okay, so this is another proof, and what's so unusual about this Regents is that having two massive proofs like this on one Regents, it's like never done. So like this was probably horrible for those students. But okay, so basically we're just going to start using the givens and see where that gives us, what that gives us. Okay, so you're told that this is an isosceles trapezoid, and that would mean that AD is equal to CB. Okay, so let's write that up. So AD equals CB, and the reason is because non-parallel sides of an isosceles trapezoid are equal. Okay, so they did that. Now don't forget, in an isosceles trapezoid, also the base angles would be equal, this one and this one. Okay, but we're going to wait and see if we even need that, but we're going to keep that in mind. Okay, next we're told with this, angle CDE, right here, is equal to angle DCE, which is this one right here. Okay, so we can mark those. Let's see what else they're telling us. AE is perpendicular to DE. So AE and DE are perpendicular. That means you're going to have a right angle there. So angle DEA, but I'm going to put this all in one line. BE is also perpendicular here. And angle CEB are right angles. And how do I know that? Because perpendicular lines form right angles. Well, if those angles are each 90 degrees or right angles, they must be equal. So we're going to write angle DEA equals angle CEB, y, all right angles are equal. Okay, so we have that. Okay, I'm going to make some room here. So it looks like we are out of givens. And if you look at the two triangles, this one here, and this one here, it looks like they're trying to lead us to proving those two triangles are equal, but we only have two things on those triangles. Okay, so I think we're going to have to use what we said before, which is that if this is a whole thing is isosceles, then these base angles must be equal. So let's write that up. So angle D equals angle C, because base angles of an isosceles triangle are equal. Okay, so let's think about this for a minute. If this angle is equal to this, and this little piece over here is equal to this little piece, then wouldn't it make sense that this piece over here must be equal to this piece? So let's write that. So angle EDA equals angle ECB. And why is that so? Because angle D minus angle CDE is equal to angle C minus angle DCE. Okay, so now just look at these two triangles right here. the yellow ones. You'll notice that you have angle, let me get another color here. Okay, so we have angle, angle, side, and we have angle, angle, side. So that means the two triangles are equal. So triangle DEA equals triangle CEB, angle, angle, side. Okay, if those two triangles are congruent, then that would mean that this side over here, EA, is equal to this side over here, EB, because CP, CTC, don't forget, corresponding parts of congruent triangles are congruent. Well, if you look at this triangle now, AEB, if these two are equal, then isn't AEB an isosceles triangle? So first we were supposed to prove that the two triangles are equal, and we did that over here. And next we're going to say that triangle AEB is isosceles. And the reason for that is if two sides of a triangle are equal, I'm going to make a little star and move up here because I have no more room. Whoop. Hey, that's the wrong thing. Okay. Then the triangle is isosceles. Okay, and that finishes all the problems from the working class.